Greetings, welcome. We're going to take a look this time at how to find an inference for a set of two independent proportions. In other words, we're going to look at the two population model, very similar to what we did back in the previous chapter when we were working with means, looking at two independent means versus paired means. Here we're just going to look at the independence case, okay? So the problem that we will use as grist for the mill, so to speak, is going to be exercise 6.29. Got that already over here in our studio. This is offshore drilling. A 2010 survey asked 827 randomly sampled registered voters in California, do you support or do you oppose drilling for oil and natural gas off the coast of California? Or do you not know enough to say? Below is a distribution of responses separated based on whether or not the respondent graduated from college. So I'll let you go take a look at the table in the textbook. I've just grabbed the relevant information we needed off of the table, which was how many of them said they did not know enough to say but went to college, and how many of them said I don't know enough to say but had no college, and then the total number of folks that were in the college column and had the total number of folks that were in the no college column. Okay, so the 438 and 389, that adds up to the 827, the total number of people. Okay, so what percentage of graduates and what percentage of non-college graduates in the sample do not know enough to have an opinion on drilling for oil and natural gas off the coast of California? Well, we'll go ahead and do this with an R chunk. We'll stick that in here for us to make our lives a little bit easier here. And we've got to do just some basic arithmetic here. So let's see. Let's go ahead and call P1, which will be the proportion for folks who had college. Let's call it PC. That makes more sense. So percentage of folks who had college, we will make that equal to, let's see, that's going to be 104 divided by 438. And then we'll do PN for the folks with no college, and that's going to be equal to 131 divided by 389. Okay, so those are percentages for each. We can go ahead and just run that chunk real quick so we can take a look at those numbers. And we'll look over here and we see that we get basically what? 24% and 34% respectively for those who have had college and those that have not had college, for the percentages of don't think they know not enough to make an opinion on offshore drilling. Okay, now part B, they just basically throw us off the deep end and say, conduct a hypothesis test to determine if the data provides strong enough evidence that the proportion of college graduates who do not have an opinion on this issue is different from that of the non-college graduates. Okay, so go through our same process, C's as usual for conducting a hypothesis test. So our first step here, part I, is going to be to state the hypotheses, and we will also check in and make sure that the assumptions are met. So state there's an O in there, isn't there? Hypotheses. And while we're at it, we will also check in and make sure that we've got the things covered. Okay, so this time, notice that we're comparing two proportions to each other. And so the null hypothesis is stating what? Well, that those proportions, we'll do in P sub college, okay, so P sub C, is what? Well, P sub C is equal to P sub N. In other words, there's no difference between the two proportions. In other words, the proportion of folks that don't know enough to make an opinion who have gone to college is the same as those that have not. So keep that in mind, because that's going to be important. We're going to need to talk about that some more as we move through this, right? So let's go back to the alternative hypothesis. And so the alternative hypothesis is what? Well, they said different. So what different means is that we don't know, but they're not the same. So that tells me that the proportion of college graduates that didn't know enough to going on there is the same as, is not equal to the folks who did not have college. Okay, so let's go ahead and we'll knit that real quick just to take a look and see how that all came out. Make sure that's all pretty because there's a little bit of LaTeX in there. Give it just a second here. Scroll on down. I have to kind of shrink out the page a bit for you. And yep, looking good, except for I got to do a little bit of spacing fix. But other than that, looking good there. I need to put in my double spaces at the end there so I get a line feed. Okay, so that's the null and the alternate hypotheses, but I do need to come in and say something about my assumptions, okay? And so the assumptions here basically is what we want to decide is whether or not we can say something about p times n, whether or not that is going to be greater than or equal to 10, okay? Now, you can just take a look at this particular problem and realize that the cells in the table, there are no cells in the table that are less than 10. In fact, they're all very large. And because of that, the success failure criteria, you can pretty much wave your hands over and say, hey, you know, got a bunch of big numbers in there. So that's going to work just fine. But as we will see, one way that you can do this also is by creating the pooled estimate of what the of p sub college and p sub n is according to the null, because according to the null those two numbers should be the same. It's just the null didn't tell us what they happen to be, and so based upon the numbers that were given to us in the table, in other words these values back up here, we can come up with a pooled estimate of what we think that proportion is going to be. So more about that in a bit, but for the moment we're going to say large sample, large independent sample according to the write-up in there, and so the success failure criteria is met also because it's big numbers. All right, okay, cool. All right, so that takes care of part one. Part two is going to be our decision rule. They didn't give us a level of significance to use, so we'll run with 5%. So our decision rule is going to be reject HO, reject the null, if the p-value is less than 5%. Okay, cool. All right, so that's our decision rule. Now we get to the fun part. We got to go calculate the test statistic and the p-value. So we need to know what is the test stat, not dat, GDAT, the test stat, and the p-value. Okay, so how do we get the p-value and the test statistic here? All right, so what we're going to need to do, let's go back over to the whiteboard for just a minute and talk about this, and we'll come back to it. We're going to have to come up with some way of calculating z. All right, now we know from our previous experience working particularly in this section with other proportions that the z-score should look not quite unlike but something similar to this. We know that z should be looking like something like p hat minus p from the null divided by the square root of p from the null times 1 minus p from the null, all of that divided by n, right? Now there's one little bit of a problem here in that we don't have any idea whatsoever what the null hypothesis is saying that value of p is. We just said that the two of them are supposed to be equal to each other. So that's not so problematic in the numerator, but it's going to be problematic in the denominator because the standard error estimate for two proportions is going to be given by the following. It's going to say, well, look, what you're going to do is you're going to take p1 times 1 minus p1, divide that by n1, and add to that p2 times 1 minus p2 divided by n2. But I have no idea whatsoever what p1 and p2 are. You know, up here in the null, well, I'm going to say, well, I know what that's going to be. I know that p of the null, the difference between them should be equal to 0, right? But I don't have the individual values where I need them over here for calculating the standard error. So what we have to do is we have to do a pooled estimate. And our pooled estimate of what p1 and p2 is going to be is simply going to be, we'll just call it p hat just for general, you want to put a little 0 down there to differentiate it, but it's the pooled estimate of p hat. And it's actually very straightforward. What we're going to do is we're going to take P1, N1 times P1, and we're going to add to that N2 times P2, and we're going to divide that by N1 plus N2, okay? Well, that's actually more complicated than it really even needs to be, because it's actually very straightforward. All I got to do is in our case, that's going to be the 104 plus the 131 divided by the two sample sizes, which was the 438 plus the 390 or 389, excuse me. Not to say 9 right there. Yes, okay. So what do we get for that? Well, we get that that's going to be 235 divided by 827. So that tells me that the pooled estimate, in other words, we're going to use this for both P1 and P2, is that P1, which is equal to P2, is going to be approximated by 28.4%. In other words, those two numbers will say, we said they were the same, so our best guess at what those are is by combining them all together and saying, well, looks like that's what they're going to be. So we're really back to the same problem that we face in every hypothesis test, and that in order to calculate our standard error, we have to use the sample data to be able to do that. And that's okay, provided that your sample size is large enough. You're going to get a good estimate of it. Okay. All right. So let's go ahead and see if we can actually calculate z now. So our z-score here, what's that going to be? Well, we're going to take p hat 1 and subtract from that p hat 2. That's our two estimators. We did those back in the earlier problem just a second ago. And we're going to say, well, subtract from that p1 minus p2. Well, that's going to end up being 0. And now we're going to divide that by, I'm going to put a little sub-zero here just so you can see that that's the p hat that I'm using. We're going to divide that by the standard error estimate that's going to be given to us using that piece of 0. And we're going to still use the same formula that I've got up there for the standard error. In other words, we're still going to use this formula for our standard error. It's just we're going to replace P1 and P2 with that p hat sub 0. So this denominator here is going to be given by p hat given from the null, 1 minus p hat from the null, divided by N1. Well, N1 in this case was 438. And then plus p hat from the null times 1 minus p hat from the null, but this time divided by 389. Okay, so I could have had the N1 and the N2 there. I started to put some numbers in. Let's go ahead and fill all the rest of the numbers in. Let's get everybody in there. So in the numerator, that's going to be what? 0.237 minus 0.337 minus 0. Where did I get the 0 from? Well, these two were supposed to be the same, weren't they? P1 and P2. And since they were the same, the difference between them should be 0. And then down here in the denominator, we should have what? 0.284. That's a 4 there. There we go. Times, well, let's see, you got to take 1 away from 0.284, right, which is 0.716. All of that divided by 438. And I'm going to add to that 0.284 again, times 0.716 again, and all that divided by N2, which is 389. Whew. Okay, well, let's go get back into R here, and let's go ahead and type that into an R chunk and actually get it to calculate that for us, all right? Okay, so let's go insert a chunk, and let's go down here, and we're going to say that Z is equal to, here we go, parentheses, 0.237 subtract, let's see, what was the next number there? Oh, 0.337. I'll put my leading 0 in there so I keep things straight here. Okay, and then that's subtract 0. Okay, now I'm putting it in there. Actually, I'm going to take it out, but we could put it in there just to signify that that was the difference between the hypothesized value of the null, but it's just going to get in the way, so let's get it out of there. Okay, so SQRT for now getting into the standard error. Okay, so now down in the standard error, we're going to have two terms that we need to put in there, so let's get in the first one. So that's going to be 0.284 times 0.716 divided by 438 plus 0.284 times 0.716 divided by the second sample size, which is 389. Whoosh. Okay, let's go ahead and run that chunk. Okay, and if we go over here and look, and we see that we're getting a z-score of negative 3.183049, blah, 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 which says that what we are pretty darn small. We are way down out over in the left-hand side. So before we go and calculate our p-value, we should definitely go draw in the standard normal distribution where that z-score goes in, just to help us see what we're actually doing with the calculation. So let's get a blank sheet here. And so let's go ahead and draw in a standard normal. Because remember, that's what our z-score is from, right? This is n of 0 by 1. And the mean is here at 0. And we got a test statistic of negative 3. What was it again? It was negative 3.183. Okay, so we're doing a two-tailed test. Remember that the alternate hypothesis here was that P college was not equal to P no college, all right? And so since we have a two-tailed test, we need to double our p-value. In other words, we need to come over here, be symmetric about it, and also say 3.183 also. So the two-tailed shaded regions here, let's go ahead and change to red. This shaded region plus this shaded region, these two together, those are going to be equal to our p-value. So the easiest way that we can calculate that is going to be using what? Well, we're going to go 2 times p-norm of negative 3.183, comma 0, comma 1. But I'm actually just going to put a z in there since I already calculated the z. No sense having to type in the number if I don't need to, okay? All right, so let's go back into RStudio and let's go do that. So getting my p-value here, I'm going to go 2 times. Remember doing the 2 times because it is a two-tailed test. Two-tailed, 2 times, okay? P-norm, and then I'm going to put in my z, comma 0, comma 1, okay? And so if I go ahead and I run that chunk, notice that I get a p-value of 0.00145, etc. In other words, I get a really small p-value. So we're on to the third step of our hypothesis test, which is to state our decision here. So what is our decision? So decision would be to reject the null hypothesis, since the p-value is less than 5%, okay? All right, cool beans, okay? So that was actually not step 3, that's step 4 there. Okay, so step 5 means what? What are we doing now? Well, we got to actually tell them what the heck all this all meant, okay? So how do we interpret this in terms of the actual test, okay? So the conclusion says there appears to be what? There appears to be a significant difference in the proportion of college grads that do not know enough about the topic. Okay, good enough. That'll work. All right. Okay, so this is the last of the lab videos. So from here, you are on your own to get going on the assignment. You take it from here using the same RMD. If you've got questions, please post those to the discussions, and I'd be happy to get back to you as quickly as possible.